When we discussed merge sort and quick sort, I mentioned that those are from the family of algorithms called divide and conquer. We have other kind of algorithms called like in the category of transform and conquer. So these group of algorithms solves a problem by transformation to either a simpler or more convenient instance of the same problem, a different representation of the same instance, or a different problem for which an algorithm is already available. To be of practical value, the combined time of the transformation and solving the other problem should be smaller than solving the problem itself. So one example of this kind of algorithm is heap sort. The idea behind heap sort is that we have a given array or a vector, and we build a heap containing the elements to be partially ordered. Then we remove them one by one. So we already in the previous video we already saw how we can build a heap from an array, and we saw how we can remove from the heap, right? So how we can dequeue from the heap, or how we can delete root of the heap, right? So in the stage one of merge sort algorithm is constructing a heap for a given list of n key values, right? So like n key values that we have in a array. And then the second stage, which is called the extraction phase, we repeat the operation of root removal, right? So like if we have a max heap, we remove the maximum number inside the heap, which is in the root. And if we have a min heap, we remove the minimum number of the heap, right, which is again like stored in the root. And we do this process n-1 times. So what we do in this process, we exchange keys in the root and in the last, which is the rightmost leaf. You saw this, like this is like in the deletion part, right? Whenever we delete the root, we exchange the keys in the root and the last or the rightmost leaf. We decrease the size of the heap by 1, and if necessary we do bubble down, right? So like we have to make sure that we reheapify the binary tree, the complete binary tree that we have. So and we do this process n-1 times. And whenever we delete the root, we keep it in a temporary variable. So we store it in a temporary variable. So although it's going to be removed from the heap, but we can store it in a temporary variable, right? And because the size of our heap is reduced by 1, it means that in our array, we have one empty spot. So the root that we deleted, we're gonna put it in that empty spot or in that hole that is available, right? And because in the max heap version, the root has the maximum number, it means that after doing that, we have the maximum number in the last element. And if we do this n-1 times, we end up with a sorted array. Advantages of heap sort. So if we ignore the constant of like proportionality and runtime efficiency, if we ignore the constant of proportionality, runtime efficiency of heap sort is of order n log n. So it is more efficient than like algorithms which are quadratic, such as bubble sort, selection sort, insertion sort. And another advantage of heap sort is that it's an in-place sorting algorithm. It means that we don't need an extra memory space. Like what we did, what we had in merge sort. So it's an in-place algorithm. This algorithm was invented by John Williams, who's like who was a Canadian scientist, like back in 1960s or 70s. So like that's another advantage of this algorithm, I guess, for us. So how this algorithm works is that first, in the first step, which is the construction step, we just do heapify. So we have an array, right? We have an array and we make it a heap, right? We saw the process for doing that in the previous video. In the previous video, we saw that there are two processes for doing that. It's top down or bottom up, right? And one of them was big O notation n log n. The other one was just big O of n, right? So like heapification from like just like using the bubble down approach is more efficient, so we do it that way. So that's going to be of big O notation n. And then what we do, like now we have a heap, right? And we know that always the root of the heap is at the first element, right? So like what we do, we remove the root, excuse me, we remove the root, right? And we replace it with the last element, and then we have to do bubble down, right? We have to find the children of this node and we go down all the way to the leaf, right? To make this a heap again, right? But because the size of heap is reduced by one, because we just removed one node from the heap, right? We have one empty spot in our array. So the root that we removed, we keep it in a temporary variable, and once we reheapified the reduced array, right? Then we insert the previous root in this empty spot, right? If we have a max heap, this root would be the maximum number inside our array. Okay, so this is like the process, like from steps 2 to step 5. So we just like you see that the array is always partitioned into two parts. One part that's heap, and the other part that is the part that we keep the previous roots, which we call it the sorted part. And we keep doing this process n minus 1 times. Okay, so we keep doing this process n minus 1 time. So like you see that like we had an original heap, right? We remove the root, right? And we reheapified this reduced heap, like this is smaller heap, and then we stored 78, which was the previous root here. And then we do the same process again. We remove 56, we make this a heap again, right? And then insert 56 at the end of the array, like after the last element of the heap. And we keep this process n minus 1 times. If we do this for a max heap, we would have, at the end of this process, we would have a sorted array in the ascending order. If we do it for a min heap, we would have it in the descending order, right? So this is one of the applications of heap. You will see that why this is an in-place algorithm, because we basically divide the array into two sections, one part that would contain our heap and the other part that would have the sorted data. This is an example showing like different stages of heap sort. So first we have our original array, right? Which is like we place it like in a, excuse me, we place it in a complete binary tree, right? And then we just like make it a heap by just like using a bubble down approach. So like this is like a heapify method that like we go bubble down, like we start from the last parent, and we do bubble down like we do for this one, we do for this one, and then like this becomes a heap as we have here. Okay, now then we start deleting the root, right? So like if we delete the root, like then 90 is gone, right? Then when 90 is gone, we're going to replace it with 30, right? Replace 30 with the previous root, right? But this is not um, like we had a max heap here, right? Like this is not a max heap anymore. So then we have to bubble down, right? So here like we find the largest child, right? Just child, like for the root it's 70, right? So 70 is gonna go up, 30 goes down, and then after reheap, like our heap looks like this. It's like 70, 40, 30, 10, 20. We have one empty spot that we place the root that we just deleted here, 90. And we do this process again. So like this time 70 is gonna be deleted, right? And eventually we're gonna place it here, right? Because we have another empty spot at this place, right? We place 70 here, right? And we end up with like if you remove 70, we're gonna replace this previous root with 20, so 20 goes up here, and then we have to reheap this again. So again, we look at the children of this root, which is 40 and 30. 40 is the largest child, so 40 is going to be compared with the root. We're going to slide 40 up, and 20 is going to go down, and 20 is bigger than 10, right? So like we can stop this reheapification process here. So after reheap, we have 40, 20, 30, and 10, right? And 70 and 90 is in the sorted section, right? Again, we remove 40, we replace it with the last element, which is 10. So 10 goes up here, right? 10 goes up here, and then 40, which was removed, it's gonna go in the empty spots that we have, right? So like because we removed the node, we have an empty spot in our array at the end of our heap, right? So like 40 is gonna be placed here. We have to reheap this again. Among 30 and 20, 30 is the largest child, so 30 is gonna go up, 10 goes down. So this is like the like bubbled down version. So like this is like a heap again, right? So we have 30, 20, and 10, 30, 20, and 10 in our heap, and 40, 70, 90 in our excuse me, in our sorted section. Again, 30 is now going to be removed, which is the new root. So 30 is going to be removed. We're eventually going to store it in the sorted section, right? When 30 is gone, the last element in the heap, which is 10, is going to replace it. So 10 goes up, 30 is gone, and 10, this root only has one child. So like, and this is like violating the max heap order property. So like we have to swap these two. 20 goes up, 10 goes down, so we have 20 and 10. Eventually we also like remove 20 as well, right? So when we remove 20, we only end up with one node in our heap, which is like this one, right? So this is like the heap, and 20, it's gonna like, because now we have an empty spot, 20 is gonna go in the empty spot, right? And at this point we don't need to remove anything anymore, right? Because like there's no point, like we already have a sorted array. So like now our array is totally sorted, right? So that's why like we have to delete only n minus 1 times, right? Because like the last node doesn't have to be deleted. Again, this shows like here, like we don't see the heap tree like topology itself, but based on the properties of the heap, we should be able to figure out what we have to do. Like we have 6 elements in our array, right? So the first stage of heap sort is heap construction. If you remember, in the heap sort, in the heapify, right? In the um, bottom down approach, when we do bubble down, bottom up approach, when we do bubble down, we start from the last parent, okay? And like we have the formulas like for the last like last parent, and like where like our leaves start and where our internal nodes end. So like this is our last parent, right? So what we have to do, like here, like we just like have to uh, like compare this node with its children, right? So like if we have like we just like basically like do this process, like we do bubble down approach, right? So like after that, 7 is gonna move down here, like, and we have 8 6 5 here, so 8 goes up here. And then um, like this is like the next parent. Again, we're gonna do um, bubble down approach, right? So like when we do bubble down approach here, like the like there's no violation of heap order property. So like you see, like there's no swapping or anything. And the last parent is the root itself, right? And we just like compare it with its children, which is 9 and 8, right? 9 is the bigger one, right? The biggest children. So like 9 is gonna go here, 2 is gonna slide down, right? And then again, like at this point, right, we're gonna compare like 6 and 5, which are the children of 2, right? So like we find their we find their like largest number, which is 6. 6 is gonna go up here, and 2 is gonna go down here, and then 2 doesn't have any more children at this point. So like we're done, like we got to the leaf. So the heap construction stage is done. Right now we have a heap. Now our array is a heap. The stage 2 is root or max removal, right? So like you see that like we remove the root, right? The root is going to go into the sorted section. The last element of the heap, it's going to replace the root. And then for this one we have to do bubble down again. So like 6 and 8 are children of 7. 8 is the bigger child, like this is the largest children, so 8 is going to go up here, okay? And so like we have 8, and then 6 and 7, 2 and 5, and then like bubble down stops at this point, right? And then like we can remove 8. We remove 8. 8 is going to go into the sorted section. The last element of the heap, it's going to replace the root, so 5 comes here. And again, we're going to compare 5 with its children. So first we have to find the largest largest child, which is 7, right? And then 7 is gonna slide up, and then 5 goes down, right? And the bubble down approach is stopped here. Bubble down iteration stops here. Like now, like we have another heap, and like 8 and 9 in the sorted section. 7 is removed, right? 7 is going to go to the sorted section. 2 is going to replace it. We compare, like we have like now only 3 nodes left in the heap. 6 and 5 are the children of 2. 6 is the largest child, so 6 is going to replace 2, right? And like this is our new heap, right? We remove 6, excuse me, we remove 6. It's going to go to the sorted section. The last element of the heap, it's going to replace the root. 5 comes here, and then we have 2 as its child, right? So like there's no need for bubble down anymore, like here, because like 5 is bigger than 2. So now 5, it's our root. We're going to remove it. It's going to go to the sorted section. 2 becomes the only node in the heap, and this is where our heap sort stops. We don't need to remove 2 anymore, like because like our array is already sorted. Here you see another example of heap sort, which is like basically the same thing that we did before, right? So like you see that like we just like transform an array into a heap, okay, store it into a complete binary tree, call heap rebuild or heapify, partition array into 2 regions, like the heap version and the sorted version. Sorry, heap region and the sorted region. Delete the root from the heap and move the root from the heap to the sorted region, and rebuild the heap or reheapify or bubble down. And we repeat this repeat from step 3. So it's like if you have a flowchart, you go back to step 3 and we do this n-1 times, right? So, and that's how like our sorted section grows and our heap goes down to only 1 node. Again, you see another example like for like both construction and extraction phase. So remember that in the construction phase, we use the method that uses bubble down because it was more efficient. You saw that it was more efficient, right? It was big O of n. So in this slide, you only see like how we convert this array into a heap, right? So like we just like make a complete binary tree first, and then like starting from the last parent, we do bubble down, right? So we do bubble down here, like let's say this version we want to create a min heap, right? So like we want to create a min heap. So then here 35 goes down, 1 goes up, the next parent is 3, the smallest child is 6, 6 goes up, 3 goes down here, right? The next child is 12, sorry, the next parent is 12, its children are 2 and 8, the smallest one is 2, so 2 goes up, 12 goes down. The next parent is 4, the smallest child of 4 is 1, right? So 1 goes up, 4 goes down, and then like 4 is already smaller than 35, so bubble down stops here. And then the last parent is 7, right, which is the root. Its children are 1 and 2. 1 is smaller than 7, 1 is gonna go slide up, right? 7, if 7 is here, like we compare 3 and 4, 3 is the smallest child, 3 goes up. And then if we compare 6 and 20, 6 is smaller than 20, so it's the smallest child, 6 goes up here, and 7 it goes like in the hole that was created here. So this is the construction phase. Now we have a heap. So then the next step, which is the extraction phase, we just like have to do n-1 removals. So we delete the root n-1 times. After deleting the root the 1 time, like we end up with like this is like after the bubble down approach, right? So this is after the bubble down approach, we end up with this heap, right? And we keep 1 in the sorted region of the array, so like it would be the last element, and we keep doing that n-1 times, and like using this method we find the array in the like decreasing descending sorted order. If you want to implement it, it's basically a combination of the methods that we already saw in the previous video, right? So like what we just like have to do, we have to build the heap, like we saw how we can build the heap, right? So like this is like the version that uses big O notation of n, and like the next thing that we have to do, we just like have to delete the root n-1 times and bubble down, right? So bubble down. So like it just like basically relies on doing bubble down. Like this one can like this is like the, excuse me, this is the non-recursive version of bubble down. In the previous video I showed you the recursive version as well. So like this is like how you can implement the heap sort. Okay, um, like like just like we don't have any visualization here. Like the only information we need to know like is that the root starts from a0. The children of ai are a2i plus 1 and a2i plus 2, assuming that the indexes start from 0, assuming that the root is at a0. Okay, and the parent of node at index I, it's gonna be a of I minus 1 divided by 2. Okay, so this also shows you the pseudocode for heap sort. So first, like, we have to construct the heap, and then we just like repeatedly delete the roots, right, n minus 1 times. So the running time of heap sort, so like you can just like break it into two parts. Like first part was construction, which was heapify. If we use the more efficient way of like making a heap out of an array, like that, we saw that previously, that the big O notation of that is big O of n. And deleting operation, like basically like we delete if excuse me, if we delete one root, it's going to be a big O notation of log n, right? We saw the delete operation in the previous video, and we're doing it like basically n minus 1 time. So like the big O notation of extraction phase, it's big O of n log n. And so like n log n is more dominant than n, so the total time is of big O notation and log n. This is like the worst case scenario. Like it can be also shown that in the best case scenario and in the average time, it's also n log n. Like the time complexity of heap sort is n log n. Compared to merge sort, both of merge sort and heap sort, they are of order n log n, but heap sort is in place, and its space complexity is basically order of 1, because like we store the deleted elements at the end, right? So like we avoid needing an extra element, extra memory location. Usually quick sort is like a preferred method over heap sort. So there is one concept, like one property associated with sorting methods called stability. I'm gonna talk about it like when I discuss radix sort in another video. So there are like, so far we have seen 6 different sorting methods: bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. So all of these sorting algorithms are comparison based algorithms, which means that like we sort the array by comparing the elements. Um, so there is a theorem that you can just prove, if you might see this in your discrete math courses, that for comparison based algorithms, the lower bound, right? So like the lower bound for big O notation is a log of, is the ceiling of log of n factorial base 2, which is like, if you follow this, it's gonna be n log n, right? So like what we achieved using merge sort, heap sort, and quick sort, it's already the it's the lower bound only for comparison based sorting algorithms. Okay, so there are other algorithms that can sort an array not by comparing elements of the array. one of the most famous ones is radix sort. So in some cases, radix sort can be faster than comparison based algorithms. So I'll make a video discussing radix sort shortly. So we'll see we'll see a comparison between radix sort and other algorithms that we have seen so far. So as a summary, among all the algorithms that we have seen so far, like we haven't seen shell sort in our courses, but like we have seen the other six, right? So like you can see the best time, worst time, average time, the auxiliary space, right? Like is it like in place or not in place? And another property, which is the stability property, um, I can mention like what the stability is. So a stability of a sorting algorithm, it means that if we have two elements in our original array with the same value, right? So let's say like both elements in the array have the same value. Let's say 10 and 10, right? Like if in the original array like this this 10 is before this 10, right? um, if in the sorted version the order of these two doesn't change, the order of these two um, equal numbers do not change, we call the sorting algorithm stable, right? The stability is going to be very important when we discuss radix sort, right? So, and you will see that some of the algorithms that we have seen so far, are not um, stable. So, for example, heap sort or quick sort are not stable. Selection sort is not stable. The other thing I wanted to mention, right? Like I have discussed why time comparison of algorithm is not a preferred way to compare algorithms, because it depends on many factors. It doesn't just like test the algorithm. It depends on the platform you're doing programming on, the hardware, software, um, the programming language you're using, and like the proficiency of the programmer. So like there are many different factors, but I also like wanted to I just like avoid this misconception that you think that like all the quadratic algorithms or all the algorithms that have the same big annotation would have the same time result, like when you want to sort an array, right? So like here, like for a specific case on a specific platform, for a specific array, some algorithms were compared. So for example, bubble sort, insertion sort, selection sort, and shared sort, which all of them have big O of n squared time complexity, right? So like this is like it shows like for a specific case, their time like to basically sort the array of a certain size. You see that like all of the times grow quadratically, right? So like all of them are quadratic, right? But because like we ignored the coefficients and we ignored the least significant terms, right? So like they're not gonna have exact time answers. Some of them are gonna be faster than the others. The same thing applies for heap sort, merge sort, and quick sort. All of them have the same time complexity, but doesn't mean that like they're gonna give us the sorted array in the same time. That's all for this